Alright, I want to look at another kind of sequential circuit. This one's going to be basically a toggle flip-flop, although I'm not going to include a T input. This is going to toggle every time that the incoming clock drops from a 1 to a 0. And we're going to build this out of 3 cells, like most of our edge trigger devices. And this will be our negative edge triggered clock, and ultimately we will have Q coming out on the bottom. Now our cell on the west and on the east will be basically recirculating, and our middle cell's behavior can be defined in 2 cases. One where we have a 0 coming into the top, and one where we have a 1 coming into the top. Now in the case where we have a 0, we're going to take the input from the west and recirculate it, and we're going to send a copy over to the east. So we have some bit value trapped between these 2 cells, and it's also being supplied to the east. In the case where our input changes from a 0 to a 1, we're going to take this bit value that's been coming back from the east, and we're going to trap that. So our output will not change, and this is our output here, Q. Our output does not change when the clock rises, but a copy of the current output value gets inverted and sent to the west. Now it doesn't appear on the output because when our input is a 1, the value coming from the west doesn't go anywhere. But now when we change the clock from 1 back down to 0, that inverted value will now get recirculated back. We've toggled the value that's trapped over here, and that gets sent through the middle cell into the cell on the east and appears as our output. If we additionally add a feedback path from the east to the south, so that whatever bit we're seeing on Q also comes out on the bottom, we now have a device that looks like this. We have 3 cells. Our clock goes in the top, and Q comes out the bottom. And we can cascade these in successive rows with the output of one stage feeding the clock of the next stage, and we get a ripple carry counter. If we use n rows, we get an n-bit counter. And the values are also sent out to the right, so we can use this in conjunction with our match column decoder and build a circuit that looks as follows. So let's say we have 4 bits. So these 3 columns worth of cells act as our counter. We drive it with a clock coming into the top, and this is now a 4-bit counter. This is least significant bit, most significant bit, and our count value is coming out of the east of this column of cells, and we can set these up to be match columns. And we can ask this to match a row of zeros. This can match a 1, this can match a 2, this can match a 3, and so on and so forth. And we take the outputs from here and we send them somewhere that we're interested in. And now every time this counter ticks, another one of these outputs will be asserted. First this one, and then this, and then this, and this, and so on. And again, this can be used in a number of cases. For example, when you have a series of cells stored in a library that you want to use to create a circuit on the fly, you could store those sequentially underneath each of these columns and use this signal to say read the truth table from that cell, send it out down a pathway, and use it to build part of a target circuit. So that's just another example of how we can put together some sequential logic and this combinational matching logic to do some interesting sequence generation.